My presentation. My name is Nils Wilhelmsen, and I am ESR number 2 within the Magister project. Today I'm going to tell you a bit about my research, which is on parameter and state estimation of thermoacoustic instabilities via distributed parameter models. The basis for my research can be summarized in the following research question. How can we estimate the states and parameters of systems suffering from thermoacoustic instabilities by combining measurement data with distributed parameter models? In other words, the aim is to investigate feasibility and design of algorithms that take time series measurement data from a combustion process as input and produce estimates of states and or parameters of the thermoacoustic system as output, using so-called distributed parameter models as the basis for algorithm design. It should be emphasized that an important part of the research process is convergent analysis, i.e., ensuring that the estimates converge to the true values given the process dynamic matches the model used. To better understand the research question, I will briefly go over some terminology. Firstly, it is important to be clear over the difference between states and parameters. Given a mathematical model of some process, the states are typically the physical quantities the model is describing the behavior of, whereas parameters are values that influence the behavior. As an example, consider a mode in a combustor described by the following harmonic oscillator. Here we see that the states are the pressure of the mode, denoted eta, and the heat release rate, denoted Q. The parameters, highlighted in red, are the damping coefficient alpha and the resonance frequency omega. Another term which is important to understand is that of distributed parameter model. The contrary to this is lumped parameter model, this being a mathematical model with a finite number of states. These can often be represented as ordinary differential equations, and the harmonic oscillator example just considered falls into this category. On the other hand, a distributed parameter model describes an infinite number or distribution, if you like, of states. These can typically be represented by partial differential equations. An example of this is the linearized energy equation, which has an infinite number of states distributed over the spatial domain. The advantage of using distributed parameter models over lumped parameter models is that with the former you must not restrict yourself to a truncated number of modes, giving you a more accurate description of your system. On the other hand, using distributed parameter models can be more computationally intensive, and the analysis techniques are often more involved and difficult. However, much progress has been made in computational power and also analysis techniques for distributed parameter models over the past decades. And the goal of this research is to leverage on that for the study of thermoacoustics. Okay. So the following 5 steps summarizes the main research methodology followed in my work. As a first step, a mathematical model describing the process is established. This could either be achieved through taking a model from the literature, or making a model using first principles, or possibly using software to find a suitable model based on, for instance, experimental or simulation data. Additionally, it must be decided where and through what means the system is sensed. After this has been established, an estimation problem can be formulated. It could be the case that the particular coordinates of the model are unsuitable for analysis. And in this case, a coordinate transformation must be found and applied to the system model. The next 2 steps are arguably the most important yet challenging steps of this research process. After having formulated an estimation problem, an implementable estimation scheme must be designed. By implementable, it is meant that the scheme only uses past and current, not future, values of measurement data, and possible known input signals as formulated in the problem statement, and produces some meaningful estimates of the desired process. This can be surprisingly non-trivial to achieve for certain setups. With the estimation scheme set up, we must analyze to what degree the estimates will be correct. Just because an estimation scheme is implementable doesn't mean that the estimates will be correct. You could even have situations where the estimate completely diverges from the true states and the algorithm blows up. So usually this step involves establishing the rates at which the estimates converge and conditions under which this is true. Lastly, after one has an implementable estimation scheme with proven convergence properties, simulations are implemented to verify this on an example. I will now go over 3 results highlights from our research. The first result is a state estimation scheme for the electrically heated vacuum tube. Here, a nonlinear model of the heat release is combined with distributed acoustics as a basis for the design. Next, a parameter estimation scheme for estimating unknown acoustic reflection coefficients in a duct in real time using a single pressure measurement is presented. Lastly, a state estimation scheme for estimating the states of a flame model and also the acoustics it is coupled to in a separate duct from where the flame is situated is presented. This could be useful in scenarios where measurements taken directly at the flame is infeasible and also takes into account thermal acoustic coupling. Okay, so firstly, vacuum tube, the aim of this estimation scheme is to estimate the pressure, velocity, and heat release rate in a vacuum tube using measurement data taken close to one of the ends of the tube. Linearized momentum and energy equations are used as basis for the distributed acoustics model, whereas lumped nonlinear King's law models the heat release rate. This results in a network model of the thermoacoustics, taking into account both distributed nature of acoustics and nonlinear nature of heat release. Using knowledge of a pressure signal from the lower boundary, we design, analyze, and implement a state estimation scheme for the vacuum tube. I will now summarize the main ideas behind the design and analysis. The diagram on the left shows the vacuum tube model transformed to Riemann coordinates and folded around the location of the heater, and subsequently normalizing the length of each spatial subdomain to 1. The observer is then designed as a copy of this plant model, but with some modifications. Firstly, at the top right of the figure, the measurement signal y is injected into the boundary. The other boundary is, however, not measured, and just using the estimated signals here can cause instabilities. To deal with this, we attempt to reconstruct the boundary highlighted by the blue oval using known signals. Noticing that the boundary conditions labeled by the orange circles contain partially the same information, the difference being the top boundary receives information, the boundary circle in green, and the bottom orange circle receives information from the measurement signal. We reconstruct then the top boundary condition with an exponentially converging error. Designing the observer in this way results in the error system structure shown on the right. We see the estimation error of U1 goes to 0 in finite time. Next, the estimate for V2 converges to its true value exponentially, feeding into the estimate for X. We can then show that the error state for X is input to state stable with respect to V2, implying asymptotic convergence for X. Lastly, the convergence of the estimates for U2 and V1 can consequently be established. I will now wrap up the vacuum tube state estimation scheme by showing output from a simulation. Firstly, on the left, we see the estimation error of heat release rate compared to 2 alternative distributed parameter state estimation algorithms for this electrically heated vacuum tube. in a simulation with perfect conditions. The two alternative algorithms do not have proven convergence in the nonlinear regime, but for this particular simulation, their performance is better than for the performance of our state estimation algorithm. Hence, it seems that for this particular problem, there is a trade-off between proven convergence and performance under certain idealized conditions. Next, the figure on the right shows the same output, but for a simulation where a modeling error was introduced into the acoustic boundary coefficient to test the robustness of the algorithms to incorrect parameter knowledge. Here we see that our algorithm has a smaller estimation error in heat release than the other algorithms. This shows that the steps taken to guarantee convergence pays off in the form of various robustness properties. I will next talk about parameter estimation of such acoustic boundary coefficients, which are often unknown or poorly known in practice and can be an important factor for thermoacoustic instabilities. As was demonstrated in the simulation output on the previous slide, correct knowledge of boundary acoustic reflection coefficients in systems susceptible to thermoacoustic instabilities can have a large impact on state estimation algorithm performance. I will here present a parameter estimation scheme for estimating such parameters in an acoustic duct that can be implemented in real time. Considering the setup shown below, the objective is to infer estimates for unknown coefficients Z0, ZL from knowledge of pressure measurement Y and acoustic forcing signal W. We seek a regressive form for the output signal so that we can write to the output signal as a vector of unknown coefficients multiplied by known signals. This will then allow us to apply standard parameter estimation schemes for systems in regressive form from the literature. The theoretical results can be summarized as follows. We define new parameters rho and q in terms of z0 and zl. The resultant regressive form then contains three unknown parameters, namely rho, q, and their product. It can then be shown that given the input signal w is sufficiently rich in frequency content, we have from applying least squares update law on the estimate of phi that the estimate of phi converges to phi exponentially. Although exponential convergence can be guaranteed in an idealized setting, our parameter vector contains three parameters, whereas we only wanted the two estimates rho and q. Therefore, after each time step, we perform a post-processing optimization step to output unique estimates for rho and q. The result just described is for ducts with straight geometry, but it should be mentioned that we can extend the results to more complex ducts with spatially varying geometry. One then gets a parameter vector with 5 unknown parameters, and a similar procedure can be applied. The parameter estimation scheme was implemented in a simulation with the straight duct. In the plot on the left, the input and output signal used are shown for a short window of time. Notice that some simulated measurement noise has been added to the pressure measurement signal. Next, on the right, we see the true parameter values in solid lines, and the parameter estimates in dashed lines. They converge, but with a slight bias due to the measurement noise. I will next present the third result highlight, which is on state estimation of a flame in an inner duct via measurements taken in an outer duct. The aim of this estimation scheme is to estimate the heat release rate together with internal states of a flame model, as well as pressure and velocity inside the acoustic ducts for a scenario where one is measuring the pressure in an outer duct but have a flame in an inner duct. This can be useful in setups where one has complex chamber geometry and it is infeasible or difficult to measure the flame directly. The flame considered is modeled by an ODE reduced order model made by Luis da Costa Ramos, ESR number 4, using ANSYS Dynarom software based on CFD data of flame. The basic idea of the state estimation scheme can be summarized as follows. We make a copy of the acoustics and flame model, but we add a so-called output error injection term, which consists of the output estimation error multiplied by a gain. For the acoustics, denoted here by W1 and W2, the gain is distributed across the spatial domain. It should be noted here that lambda1, lambda2 model the speed of sound in the duct, while sigma 1, sigma 2 models geometrical variation in the duct. For the flame, on the other hand, one has a vector valued gain L, with dimension equal to the number of internal flame states in X. The estimate of the heat release rate is then computed according to the fourth equation. We can prove that, given P1, P2, L, chosen in a particular manner, we have expressions to calculate. Exponential convergence of the estimation error is guaranteed in a linear regime. We are, however, currently still in the process of extending the design and analysis to the nonlinear regime. Although we don't have convergence results for the acoustic ducts coupled with nonlinear flame model, the linear state estimation algorithm was tested on the nonlinear flame in simulations. The plot on the left shows the heat release rate versus the estimate. As can be seen, the estimate tracks the heat release rate fairly well throughout the simulation. The estimation error is shown in the plot on the right, where we see the error converges to zero eventually. Now, when it comes to how my project is related to other Magister ESR projects, there is at least a connection with the following two. As mentioned previously, ESR 4 designed the flame model I used in the third result highlight I presented. Furthermore, we have a common supervisor. A second connection is with ESR 8. The problems we are considering are similar in the sense that they are both based on combining measurement data with physics-based models. However, completely different techniques and approaches are considered. Here are publications we have produced that have gotten published so far. For general dissemination, there are some contributions available on the Magister website.